Welcome to The Explainer. Today, we are tackling maybe the biggest question of all. How did life actually begin? It's not just a biology question. It pulls in chemistry, physics, and even philosophy. And yet, it seems totally impossible to answer, right? But what's so cool is that if we look at it from three completely different angles, we're talking statistics, information theory, and straight-up chemistry, we can actually start to build a picture of how you go from just stuff to something that's alive. All right, so here's how we're going to tackle this. First, we'll look at a pretty wild statistical clue that says life might be super common. Then, just to keep things interesting, we're going to hit a wall, a mountain of information that makes life seem basically impossible. After that, we'll get our hands dirty with some real-world chemistry from early Earth. And finally, we'll see if we can make these totally opposite ideas, well, make sense together.
So let's jump right in with a pretty bold idea from a physicist named Daniel Whitmire. His whole argument is that the fact that we're even here, thinking about this, that's not just a fluke. He says it's actually the biggest clue we have. It's evidence we can use to figure out the odds.
Okay, so the heart of this idea tackles something called the problem of old evidence. It sounds complicated, but the old way of thinking was kind of like this. Well, life is here on Earth, so the probability of life happening on Earth is 100%, duh. But if you say that, you can't really learn anything new about how likely it was to begin with. It's kind of like a catch-22.
But here's the clever bit. It's all about reframing the question. See, the old argument, which you see on the left, basically says, we're here, so we're here. End of story. We don't learn anything. But the new approach says, whoa, hold on. Let's pretend we don't know the outcome. Let's go back in time and ask, what were the odds before it happened? And that one little change, it turns our existence from a boring fact into a powerful piece of data.
Think about it like this. It's like you walk into a room and see a coin that's already landed on heads 3 times. The old logic would just shrug and say, yep, that happened. But wouldn't you be a little suspicious? The right way to think about it is to ask, what were the chances of that happening with a normal coin? It's only 1 in 8. That's a huge clue that maybe, just maybe, the coin isn't fair. The outcome, even though it's in the past, is telling you something really important. So how does this coin flip idea connect to life on Earth? Well, Whitmire brings up this concept called the independent timescale argument. It goes like this. The time it takes for life to get started, that's all about chemistry. But the time a planet can support life, that's all about the physics of its star. These 2 clocks are running on completely different mechanisms, so it would be a crazy coincidence if they were about the same length. One has to be way, way shorter than the other. And this is where it gets really mind-blowing. When you run the numbers with this new logic, you get this. A probability of over 91% that the time needed for life to start is way shorter than the time a planet is habitable. What does that mean? It means that if you have a planet like Earth, life probably isn't some 1 in a trillion shot. It's likely to happen and happen relatively quickly. Okay, so life is easy. The stats say so. We can all go home now, right? Well, not so fast, because now we have to look at this from another angle, thanks to Robert Endres. And this angle, it shows us a hurdle so massive it makes life look pretty much impossible. Let's talk about information. See, the real problem isn't just having the right ingredients, it's having the recipe. And what a recipe! The amount of information needed to build even the simplest possible cell, it's estimated to be about 1 billion bits. To put that in perspective, that's like the code for a super complex computer simulation. Trying to get that much information to assemble itself by pure chance is, well, it's just staggering. And this melting library analogy is just perfect. Imagine you're in a library, but every book you pull off the shelf literally self-destructs in 24 hours. Your job is to build the instruction manual for life from these dissolving books. It's an insane race against the clock. You can't just find the information, you have to grab it and save it before it disappears forever. And this information isn't just one thing. It's got layers. You've got the genetic code, the DNA. That's kind of like the basic data file. But then you have the structural info, how all the proteins fold into these incredibly specific 3D shapes. That's a much bigger problem. And then the biggest of all is the dynamic information. That's the software. It's the timing, the coordination, the program that makes the whole machine actually run. So what this all points to is this could not have been a random process. No way. If you were just randomly trying combinations, taking one step forward and maybe one step back,
the time it would take to stumble upon a working cell is trillions of times longer than the entire age of the universe. It's just not possible. Something had to be pushing the process in one direction, towards more and more complexity.
Okay, so where are we? We have one argument that says life is easy and another that says it's basically impossible. What gives? Well, the tiebreaker might just come from the ground itself, from geochemistry. Work by Craig Walton really forces us to stop thinking in abstracts and ask a very practical question. What could really happen in the messy, chaotic soup of early Earth?
He calls this idea interference chemistry. And it's simple, really. The environment isn't just a passive container for your experiment. It gets involved. It interferes. Sometimes that interference is good. It helps the reactions you want. But sometimes it's bad, and it wrecks everything. So for life to start, you don't just need the right ingredients. You need the right place. A place where the good interference wins out. Let's take a super important example, making RNA. Here are the basic chemical steps you'd need to take. But look closely. Every single step is what's called a dehydration reaction. That means to build the chain, you have to kick a water molecule out. And that, my friends, is a massive problem on a planet covered in, well, water. And here we have the great paradox of the origin of life. You know, when we look for life on other planets, what's the first thing we look for? Liquid water. It's the solvent of life. But chemically speaking, it's also the enemy of creating life. Trying to build these long molecules in water is like trying to build a sandcastle in the surf. Water wants to tear them apart. So the big problem wasn't finding water, it was finding a way to get rid of it, at least temporarily. So how in the world could this have worked on the early Earth? Well, there are a few ideas. You could have a big pond that dries out and then gets wet again. That works, but it's messy. You get all these minerals forming that can trap your precious molecules. Okay, what about using a different liquid, one that isn't water? Well, that tends to create a sticky, useless tar. But then there's this third option, and it looks really promising. Microenvironments. We're talking about tiny little pockets, like pores in a rock or even the surface of a water droplet. These spots can get wet and dry out really fast, solving the water problem without all the other messy side effects. So, where does that leave us? How do we put all this together? We have to stop seeing these three ideas, the statistics, the information, and the chemistry, as separate arguments. They're not. They're three sides of the same coin, three pieces of the same puzzle, and they actually fit together perfectly. Here's how it all locks in. The statistics tell us we're looking for something common, something that happens fast. The information problem tells us it can't be random. It has to be a process with a built-in direction, something that keeps pushing towards complexity. And the chemistry tells us where this magical process could happen. It points us to very specific little spots that can solve that big water problem. When you put it all together, it's like we have a brand new treasure map. It takes this huge philosophical question, how did life begin, and turns it into a practical, scientific search. A search for a planet, or even just a tiny spot on a planet, that checks all three boxes. A place that is statistically likely, informationally guided, and chemically perfect. It suggests that life wasn't a single lightning strike of a miracle, but something far more interesting. The solution to three incredibly deep puzzles, all at once.